Let me ask you something strange. Right now, something is happening inside your skull that nobody on earth can explain. I mean that literally. I'm not being dramatic for effect, although I am a little dramatic, I'll admit that. But I mean it precisely as a scientist. There is a process happening behind your eyes at this moment, and not one of us, not the greatest physicists alive, not the most brilliant neuroscientists with their billion-dollar machines, not the philosophers who've been arguing about it for 2,000 years. Nobody can tell you why that process produces the thing you call experience, why it feels like something to be you, why the lights are on, why when light of a particular wavelength hits your retina, you don't just process information about that wavelength, you see red, you feel red, something happens. And that something is the most baffling, most embarrassing, most wonderful unsolved problem in all of science. And here's the funny part, the part that should make you laugh and squirm at the same time. Physics, the most successful descriptive tool human beings have ever invented, the theory that predicted the electron's magnetic moment to 11 decimal places, the theory that described how stars are born and how they die, the theory that gave you transistors and lasers, and the bomb and the microwave oven, that same physics, when you ask it about consciousness, looks back at you with a perfectly blank face and says, I have absolutely no idea what you're talking about. That should bother you. Let me tell you why it bothers me. I've spent my whole life doing physics. I love physics the way some people love music or wine or a good argument. I love it because it works. I love it because when you set up the equations honestly and follow them wherever they go somewhere true. They go somewhere real. Nature does not lie to you. Nature is not polite, and she is not cruel. But she is extraordinarily honest. You can trust the equations, and yet here you sit, conscious, experiencing, and the equations have nothing to say about you. Not because we haven't tried hard enough, not because we need a better computer, but because there is something about experience itself that seems to slip right through the nets of physics. And I want to talk to you about why that is, and why I think it points to something genuinely, thrillingly unfinished about our picture of the universe. Let's start simple. Let's start with what physics actually says. If you ask a physicist, a very honest physicist, to describe a human being, here is what she will tell you. She will say you are a collection of atoms, about 7 octillion of them, give or take. These atoms are mostly empty space. The nucleus of each atom is so small compared to the electron cloud around it, that if you blew the atom up to the size of a cathedral, the nucleus would be about the size of a fly. You are mostly empty space. You are a very thin fog of particles with enormous gaps between them, interacting through fields, the electromagnetic field, the weak nuclear force, the strong nuclear force, and gravity. That's it. That's everything physics has to offer on the subject of Richard Feynman standing in front of an audience. A pattern of particles and fields, evolving in time according to equations that are, at their deepest level, the equations of quantum mechanics. Now, here is what those equations tell us about what your particles are doing. They're vibrating. Atoms in your body are in constant, ceaseless thermal motion. The molecules in your brain are colliding, bonding, separating, sending electrical signals down channels made of protein. Neurons fire. Sodium ions rush through membrane gates. Potassium ions drift back. Electrical gradients shift and ripple across the surface of cells, and the ripples propagate through networks, and the networks interact in extraordinarily complex ways. All of this is physics. All of this is describable, in principle, by equations. Beautiful equations. Equations that Schrödinger and Heisenberg and Dirac worked out. Equations that have never once been wrong when we've checked them carefully. So, where are you in those equations? Don't shake your head. I'm asking you directly. You're sitting there right now experiencing this lecture. You can feel the chair. You can hear my voice. You are aware that you are aware. Where is that in the equations? Show me the term in the Hamiltonian that corresponds to the redness of red. Show me the wave function that contains the feeling of wondering. Show me the differential equation whose solution is the experience of being curious. It's not there. I don't mean we haven't found it yet. I mean there is a very deep, very serious question about whether it could be there. And this is what philosophers call the hard problem of consciousness, a phrase coined by the philosopher David Chalmers in 1995, though the puzzle itself is far older. The easy problems of consciousness, and they're not easy, don't get me wrong, they're fantastically hard. It's just that they're easy compared to the hard problem. The easy problems are questions like, how does the brain integrate information? How does it direct attention? How does it distinguish waking from sleep? These are hard scientific questions, but they are, in principle, answerable by discovering the mechanisms. Find the right circuits, map the right connections, and you explain the behavior. But the hard problem is different. The hard problem asks, even if you explain all the mechanisms perfectly, why is there any experience at all? Why isn't it all just computation in the dark, with no lights on, with nobody home? Let me give you a thought experiment that Chalmers made famous, though I'm going to tell it my way. Imagine I build a robot, a very sophisticated robot. This robot has cameras for eyes and microphones for ears. It has a computer brain with, let us say, 1 billion times more processing power than the human brain. I program it with every piece of physics and chemistry and neuroscience we know. I wire it up so that when light of wavelength 700 nanometers hits its cameras, it does everything a human being does when they see red. It labels the object red. It distinguishes it from blue and green. It integrates this information with memory and context. It produces appropriate behavior. It says, that is red. It avoids red warning signs. It prefers red apples to green ones when apples are programmed as desirable. It does everything you do. Is it seeing red? Is there something it is like to be that robot in that moment? You don't know. I don't know. Nobody knows. And here's what makes this so delicious and so maddening at the same time. There is no physical measurement you could perform on that robot from the outside that would settle the question. You could scan every transistor, you could map every information flow, you could run every test, and you'd never know, because the hard problem is precisely that experience, if it exists, is invisible from the outside. You can only know your own experience directly. You infer that other people have experiences because they're similar to you and you have yours, but you can't prove it, you can't measure it, you can't put it in an equation. This was, by the way, the thing that drove the great philosopher and mathematician Gottfried Leibniz absolutely crazy back in the 17th century. He had this wonderful thought experiment. Let's say we could scale up the brain to the size of a mill, a big watermill, so we could walk around inside it and see all the gears turning and the wheels spinning and the levers moving. We're walking through this enormous mechanical brain, watching every part do its job. And Leibniz says you would never find perception in there. You would find mechanisms. You would find parts pushing other parts. But the experience itself, that would be nowhere to be seen. He was describing the hard problem 300 years before Chalmers named it. Now, you might be thinking, and this is a very reasonable thing to think, many smart people think it, you might be thinking, Feynman, you're making a mountain out of a molehill. The brain is just very complicated. Consciousness is just what it feels like from the inside when neurons do their thing. When we understand the neurons well enough, the mystery will dissolve. This position is called functionalism, or sometimes physicalism, and it's held by a lot of perfectly serious scientists. Francis Crick, who helped discover the double helix, and there's a man I admire enormously, a great scientist, spent the last decades of his life arguing that consciousness is just neural correlates, just certain patterns of activity in certain parts of the brain, and that's all. Find the patterns, solve the problem. I don't want to be dismissive of this view. It might be right, but I want to point out that it hasn't worked yet, and not for lack of trying. We have been mapping the brain for decades with increasing sophistication. We have fMRI machines that can watch the blood flow to different regions as you think different thoughts. We have electrode arrays that record from hundreds of individual neurons simultaneously. We have a map of every synapse in the tiny brain of a worm called C. Elegans, all 302 neurons, every connection, and we still don't know how to generate experience from those connections. We know which neurons fire when a C. elegans smells food. We don't know if it smells anything. Here is the thing that makes the hard problem genuinely hard, and not just temporarily hard, not just hard the way factoring large numbers is hard before you find the right algorithm. The hard problem has a peculiar structure. All the other problems in science are, at bottom, problems about the objective, the third person, the publicly observable. You ask, what are the laws governing this phenomenon? And you look at the phenomenon from the outside, you measure it, you find the regularities, you express them mathematically. That method has worked unbelievably well for 400 years. It gave us Newton and Maxwell and Einstein and quantum mechanics, but consciousness is, by its very nature, first person. It's what things are like from the inside. And there is a deep question, genuinely deep, not resolved. I'm not trying to pretend otherwise about whether a fundamentally third-person methodology can ever fully capture something essentially first-person. It's a bit like trying to describe the color red to someone who has been blind from birth. Not the wavelength. I can tell you the wavelength. 700 nanometers, no problem. Not the physical properties. I can tell you everything about how photons of that energy interact with cone cells in the retina. All of that is third person. All of that I can describe beautifully. But the experience of redness, what it's actually like to see red that seems to require being a certain kind of system from the inside. You can't get it from the outside no matter how complete your description. Now let me tell you about something real, something that happened in physics, because I think it's the closest analogy we have to this puzzle, and most people have never heard it described this way. In the early days of statistical mechanics in the 1870s and 1880s, there was a young Austrian physicist named Ludwig Boltzmann who had a beautiful idea. He understood that heat temperature was not a fundamental property of matter. It was what it felt like macroscopically when the individual molecules were moving fast. Temperature was average kinetic energy. Cold was molecules moving slowly, jiggling gently. Hot was molecules crashing around violently. This was a profound insight. He could derive the laws of thermodynamics, the laws governing heat and entropy and irreversibility from the underlying mechanics of molecules. He called this statistical mechanics, and it was one of the great achievements of 19th century physics. But here's the thing that tore Boltzmann apart for years, the thing that his critics hammered him with constantly. The underlying laws of mechanics, Newton's laws, which govern the molecules, those laws are time-symmetric. Run the movie forward or backward, they work exactly the same. But the macroscopic behavior, the behavior of heat and entropy, is not time-symmetric. Heat flows from hot to cold, never the other way. Entropy always increases. The macroscopic laws have an arrow of time, the microscopic laws don't. How does the arrow appear? Where does it come from? Boltzmann's answer, which was correct, was that it's statistical. There are vastly more disordered arrangements of molecules than ordered ones. So systems tend to evolve toward disorder simply because there are more ways to be disordered than ordered. The arrow of time is a statistical fact, not a fundamental one. Why am I telling you this? Because I think consciousness might be like time's arrow. I think we might be looking for it at the wrong level. Just as you cannot find the arrow of time in the equations for individual molecules, you have to step back and look at the statistics of enormously many molecules perhaps you cannot find experience in the equations for individual neurons. Perhaps experience is something that emerges at a level above the physics, not because it violates the physics, but because it is a description of a pattern that the physics doesn't naturally express. Now, there are several serious proposals on the table for how something like this might work, and I want to walk you through the main ones because I think they're fascinating and because I think you deserve to know what's actually being proposed, not just what popular articles tell you is being proposed. The first proposal is what I'd call the computational view. This is the view that consciousness is information processing specifically, that any system that processes information in the right way will be conscious. This is associated with the work of people like Giulio Tononi, who has developed something called integrated information theory, or IIT. The central idea is that consciousness corresponds to integrated information, information that is generated by the system as a whole, over and above the information generated by its parts independently. Tononi gives this a mathematical symbol, phi, and the claim is that systems with high phi are conscious and systems with low phi are not. A connected network of neurons has high phi because the neurons are all talking to each other and the whole generates more information than the sum of the parts. A loose collection of independent calculators has low phi because they're not integrated, each does its own thing. This is a serious theory. It makes predictions. It says, for instance, that the cerebellum, the part of your brain with more neurons than the rest of the brain combined, should contribute less to consciousness than the cerebral cortex because the cerebellum has a more modular, less integrated architecture. And this actually seems to be supported by evidence damage to the cerebellum impairs coordination but rarely affects consciousness directly. But IIT has a strange consequence that makes a lot of people uncomfortable. If consciousness is integrated information, then certain systems that we don't normally think of as conscious, certain simple networks, possibly even certain physical systems at large scales might be somewhat conscious. And certain systems we might expect to be conscious if they are the right kind of information processing might not be. This is not a reductio ad absurdum. This is just where the theory goes. And the discomfort it produces tells you something about how deep our intuitions about consciousness run and how poorly calibrated those intuitions might be. The second proposal comes from quantum mechanics, and I have to be very careful here because this is an area where a great deal of nonsense is produced alongside a small amount of genuine scientific inquiry. Let me separate the two. The nonsense version goes like this. Quantum mechanics is weird. Consciousness is weird. Therefore, quantum mechanics causes consciousness. This is not an argument. This is what we call in the trade a non sequitur. Weirdness is not a conserved quantity that flows from one mysterious thing to another. The genuine scientific version is more specific. Roger Penrose, an extraordinarily gifted mathematician, the man who worked out the geometry of black holes with Stephen Hawking, a serious thinker, has proposed, with the biologist Stuart Hameroff, that consciousness arises from quantum processes in structures inside neurons called microtubules. These are tiny protein tubes that form the skeleton of the cell. Penrose and Hameroff argue that the microtubules can maintain quantum superpositions, the strange state where a quantum system is in two states at once, and that the collapse of these superpositions is connected, in some deep way, to moments of conscious experience. I should tell you what I honestly think of this. The physics of quantum superposition is perfectly real, don't get me wrong. Quantum mechanics is not in question. But whether biological microtubules can maintain quantum coherence at body temperature in the warm, wet, noisy environment of a living cell long enough to matter for neural computation, that is deeply questionable. Quantum coherence is famously fragile. It survives in carefully isolated laboratory conditions at temperatures near absolute zero. Maintaining it in a neuron at 37 degrees Celsius, surrounded by a sloshing sea of water molecules, seems, to put it charitably, like a tough sell. The evidence for it is currently weak. I won't say it's impossible. I don't like saying things are impossible when I haven't done the calculation, but it's not where I'd put my money. There's a third proposal that I find the most intellectually honest and also the most radical, and that's a position called panpsychism. Now, before you laugh, and I can see some of you already smiling, let me tell you that this position is held by some very serious philosophers and even a few physicists. The idea is roughly this. Consciousness, or something like it, something proto-experiential, is a fundamental feature of reality, not something that emerges from matter in the right arrangement. Something that matter has, in some form, even at the most basic level. Electrons don't see or think or feel. We're not saying that. But perhaps there is something it is like to be an electron in a very thin, very simple, very primitive sense, and what we call human consciousness is what that primitive proto-experience looks like when it's organized at enormous scale and complexity. This sounds crazy. I know it sounds crazy. It sounded crazy to me the first time I heard it carefully articulated. But consider, the alternative is to say that at some point, as you add more and more neurons to a system, consciousness suddenly appears from nothing. It's not there with one neuron. It's not there with 10. It's not there with 1,000. And then at some point, billions! And suddenly there's someone home. The sudden appearance of experience from pure mechanism feels almost as strange as the panpsychist alternative. At least panpsychism doesn't have the magic threshold problem. It just pushes the mystery down to the very bottom. Now I want to tell you something about the history of science that I think is directly relevant here, and it's a story that most physicists know but rarely tell to general audiences. In the 17th century, people were very puzzled by gravity. Newton had just worked out the universal law of gravitation, and brilliant, magnificent, one of the great intellectual achievements in human history. But there was something about it that bothered people enormously. Gravity, in Newton's theory, acts instantaneously across empty space. You remove the sun from our solar system, and the Earth instantly knows, instantly feels the change and begins to travel in a straight line. But how? How does the Earth know the sun is gone? There is nothing in between. There is just empty space. And through that empty space, somehow, the influence travels instantaneously and precisely. Newton himself called it action at a distance, and he was embarrassed by it. He wrote famously, "I feign no hypotheses," he meant. I'm not going to pretend I know how this works. I have the equations, I don't have the mechanism. 200 years later, Faraday and Maxwell filled in the gap with the concept of fields, the electromagnetic field, the gravitational field, the idea that space is not empty, that it is a medium, a fabric, it carries influences from place to place. The mystery of action at a distance dissolved, not because we stopped asking the question, but because we discovered something new about the nature of space, that it has structure, that it is a physical thing, that it does something. My feeling, and I want to be very careful here, because this is feeling, not physics, not established result, just an old physicist's intuition. My feeling is that consciousness is waiting for its fields theory. There is something we don't yet understand about the relationship between physical processes and experience. Not because experience violates physics, not because there is some mysterious non-physical soul floating around, but because our current framework of physics is incomplete in a way we haven't fully grasped. Just as Newtonian mechanics was complete enough to put the planets in the right orbits, but was missing something fundamental about the structure of space, our current physics is complete enough to predict everything we can measure from the outside, and yet is missing something about the nature of what it is to be a physical system from the inside. And here's what I find genuinely exciting about this. Not frustrating, exciting. Because when I look at the history of physics, the places where something doesn't fit, the places where the equations give you a blank stare, those are the places where the next revolution is hiding. The ultraviolet catastrophe, the complete failure of classical physics to describe how a hot object radiates light, that was the crack in the wall that let in quantum mechanics. The constant speed of light, regardless of the observer's motion, that was the crack that let in special relativity. The anomalous perihelion of Mercury, the orbit of Mercury that didn't quite match Newton's prediction, that was the crack that let in general relativity. The places where physics fails are not embarrassments, they are invitations. Consciousness is the biggest crack I know of. It is the most beautiful failure of the most successful theory we have. And when a theory fails so completely, in such a specific and interesting way, that's when you know you're standing at the edge of something genuinely new. Let me try one more thought experiment, because I think it will crystallize something important. Consider this. You are dreaming. While you dream, your brain is generating, creating, producing, synthesizing an entire world. Colors, sounds, textures, smells, people, conversations, events. A complete, apparently coherent reality. And none of it is real, in the sense that none of it corresponds to anything happening outside your skull. The dream world is entirely a production of your nervous system. And yet it is experienced. It feels exactly as real as this room, while it's happening. The experience is indistinguishable from the inside, from waking experience. You don't know you're dreaming, usually, until you wake up. Now ask yourself, what is the relationship between the physical activity in your sleeping brain and the dream world you experience? There is clearly a correspondence. Certain activities in certain brain regions produce certain kinds of dream content. We know this much, but the relationship between the neural activity and the experience is not at all well understood. The physics is in the brain. The experiences of a world that doesn't exist, and the passage from one to the other, from the pattern of neuron firings to the felt world of the dream, is entirely mysterious. But here's the thing that should really get you. If dreaming is possible, if your brain can generate a full, detailed, apparently real world entirely from its own internal dynamics, then what is the guarantee that waking experience is any different? Not that it isn't real. I'm not going down that rabbit hole. We're not doing Descartes tonight. But it reveals something important. Experience, whatever it is something your brain constructs. The redness of this, if there was something red, is not in the world. The redness is in you. The world has wavelengths. You have red. The sound of my voice is not in the air. The air has compression waves. You have sound. The world, as you experience it, is, in a perfectly precise sense, a model, a construction, a representation. And the question of why that representation is experienced, why it doesn't just happen in the dark, why there is a feeler of the feeling, that is the hard problem, and it is unsolved. Now, I want to tell you why this matters beyond just curiosity, beyond just the pleasure of a good puzzle. There is a view that has been gaining ground in cognitive science and philosophy of mind associated with people like Daniel Dennett, in which consciousness is, in a sense, not quite what we think it is. Dennett argues, and he argues it brilliantly with great logical care, so I want to characterize it fairly, that many of our intuitions about consciousness are simply wrong. That there is no single place in the brain where experience happens. That the unity and continuity of consciousness are illusions generated by the brain's narrative machinery. That when you think you're having a vivid, unified experience, what is actually happening is that your brain is confabulating a story after the fact, editing the timeline, creating the sense of a continuous self where there isn't really one. This is genuinely unsettling. And I want to tell you that I think there is real evidence for parts of this. The experiments by Benjamin Libet in the 1980s are among the most disturbing in the history of neuroscience. Libet asked subjects to flex their wrist whenever they felt like it, and to note the position of a clock hand at the moment they felt the urge to move. Simultaneously, he recorded electrical potentials from the brain using electrodes on the scalp. And what he found was this. The brain electrical activity that precedes the movement, what's called the readiness potential, begins about half a second before the movement, which is not surprising. But the conscious awareness of the intention to move the moment the subject noticed the urge comes about 300 milliseconds after the readiness potential begins. The brain starts preparing the movement before you're aware of deciding to make it. The free will implications of this experiment have been debated endlessly, and I don't want to get into that particular sinkhole tonight. But what it reveals is something important. Your brain is doing things before your conscious experience reflects them. The timing is off in a way that suggests experience is not running the show, at least not in the way you think it is, at least not always. Your conscious experience of making a decision may be in some cases more of a readout than a driver, a report rather than a command. This should not make you despair. I want to be clear about that. I know it sounds like I'm dismantling something precious, but I think the opposite is true. I think what these puzzles reveal is that consciousness is more interesting than the simple story we tell ourselves. We thought we knew what it was, a little person sitting behind our eyes, watching the world, pulling the levers. Turns out it's something far stranger and more complex and more beautiful than that. And the fact that we don't understand it yet, the fact that the best tools we have, the equations of physics, the measurements of neuroscience, the logic of philosophy, all of them together still can't fully crack it, that tells me it's real. It's not going away. And when something real stubbornly refuses to yield to your tools, you don't abandon the problem. You build better tools. That's what science is. That's what it has always been. Not a body of answers, a method of getting less wrong forever. I've been a physicist for most of my life, and I've learned a lot of things, and I've been wrong about a lot of things. And I've discovered that being wrong is not the catastrophe. It sounds like it's the engine. But there's one thing I've been consistently surprised by across decades of doing this, and it's the thing I want to leave you with tonight. The universe did not have to be interesting. There was no requirement in the laws of physics that reality be arranged in such a way that creatures would evolve who find it beautiful. There was no guarantee that the same neural machinery that evolved to find ripe fruit and avoid predators would turn out to be capable of calculus, of quantum mechanics, of Beethoven, of love poems and particle accelerators and the theory of evolution. That's strange. That's a remarkable and deeply non-obvious fact about this particular universe. And even stranger, and I mean genuinely, profoundly stranger, somehow the universe generated out of hydrogen and time, something that sits here and wonders about itself, something that is not content to simply exist but needs to understand why it exists. You are a collection of atoms that has spent 14 billion years of cosmic evolution arriving at the ability to ask what atoms are. You are matter that has become curious about matter. The universe has bootstrapped itself into self-awareness, and that self-awareness has noticed the bootstrapping and is now very puzzled by it. I don't know why that is. I don't know what it means. I don't know whether the equations of physics will ever capture it. But I know this. The question is real. The question is serious. The question is as hard and as beautiful as any question we have ever asked. And the fact that we are here, confused, conscious, wondering, is not a problem to be dismissed. It's the most important thing we have to figure out. You came in here today as a person who knew they were conscious. You're leaving as a person who maybe isn't quite sure what that means. That's not a failure of the evening. That's the beginning of real thinking. Hold on to that strangeness. Don't let it go. Because somewhere in that strangeness, if we're lucky and if we're honest and if we're patient, the next great revolution in our understanding is waiting. And it is looking back at you